To get a better idea of what 95% confidence means, we're going to use the Simulating Confidence Intervals applet. And this example is in terms of proportions. I'm going to talk in terms of proportions, categorical data, but the main principles are the same for means. So over here you'll see that this applet uses pi to represent the population proportion, n is the sample size, and then we can decide how many intervals to simulate at once. So I'm going to start with just one and click sample. So we're assuming right now that the true population parameter is 0.5. But notice that in this sample, we didn't get exactly 0.5. The sample proportion was 0.45. So that's why the dot is a little bit below 0.5. So the sample proportion is a little below the population parameter. This green line represents the margin of error. So we start with our sample proportion p hat, we add the margin of error to each side. So in this case, by the time you add the margin of error, you do capture the true parameter. That's what we want. So let's do more intervals, maybe 10. So we notice that we're getting different sample proportions each time, right? That's sampling variability. We don't expect it to come out as exactly 0.5 each time. But for all of these, by the time we've added the margin of error to each side, we do capture the true parameter. Let's keep going and do more. So now we see that a few of these are red. So if you look at the ones that are red, this is where the sample proportion falls pretty far away from the population parameter. So this is, nothing has gone wrong, this is just random chance sampling variability. But in those cases, it's far enough away that even after you add the margin of error, you still don't reach the true parameter. So how often do we capture the true parameter and how often do we miss? That's actually where the confidence level comes in. So here we've been calculating 95% confidence intervals. And if we look at the running total here, it's very close to 95% of them that capture the true parameter. So in other words, about 95% of these intervals are green and 5% of them are red. So let's summarize this in your notes. So we started off, we pretend that we know the population parameter. So we pretend that we know the population proportion. And in this case, we were assuming that the population proportion was 0.5. So that's where this middle line comes from, is that we're assuming right now that we know what the true parameter is. And then for every sample, we end up with a dot with lines on each side. So the dot here represents the sample proportion, so this is your p hat value. And then you add and subtract the margin of error to each side. So the margin of error is only half the length of the interval. The margin of error is the part on each side. So looking at this picture, we notice that most of these are green, meaning most of them do capture the parameter, which is what we would want. We want to have the parameter inside our confidence interval, but a few don't. So these red ones don't. This is where we just happen to get a sample proportion that was kind of far from the true parameter, so the margin of error in those cases was not enough. So this is sort of where the confidence level comes in. So when your confidence level is 95%, which is what we have here, when your confidence level is 95%, that means that the interval captures the true parameter 95% of the time. So in other words, we could say it captures the true parameter for 95% of samples. Right? These are all showing confidence intervals that you would calculate from different random samples. And the percentage of, quote, successful intervals, the ones that capture the true parameter, that should be pretty close to your confidence level, at least in the long run if you do a lot of intervals. But this is just a simulation. So let's think about what we have in real life. In real life, we're not collecting a bunch of different samples and calculating a bunch of different confidence intervals. In real life, you would only take one sample, right? You'd use your resources, collect the largest sample you can, but you would collect one sample, and then based on that one sample, you would calculate one interval. So we're not going to have in real life this set of 100 or 1,000 confidence intervals, we're just going to have one. So then what is the point of this simulation? The point is the simulation shows that the formula works most of the time. So we've shown that the formula works most of the time. So in this case, we were doing 95% confidence intervals. So we've shown that 95% of the time, the interval is going to capture the true parameter. So then when you only have your one interval, you can be pretty confident that you have the parameter because you know that this process works 95% of the time. So that's what we mean when we say 95% confidence. And our interpretation is we're 95% confident that our parameter, whatever it is in context, that the parameter in context is between blank and blank. And you're plugging in your two endpoints there. So in a later activity, you're going to be asked to interpret some confidence intervals. It may help to come back to this applet and think about what 95% confidence means. You can also change the values. You can change the sample size, you can change the confidence level, and see what happens to the intervals as you do that.